right, welcome to the last talk of, well, certainly not least. I've been looking forward to Justin's talk for some time. Thank you for agreeing to give a talk. Thank you. So Justin Wilson is a recently joined LSU as a faculty member, and that's that. Right? But also has some overlap with quantum computing and quantum innovations. That's very interesting for us. And he'll tell us about some things with random quantum circuits.
Thanks, Mark, and I really appreciate the invitation to talk here. It's been very interesting hearing what everyone's working on and thinking about. So yeah, as Mark said, I'll be talking about criticality and multifractality and continuously monitored random quantum circuits. I'll sort of unpack what that means as I go along. But first, let me just acknowledge my various collaborators and sort of the papers this is based on. This is done with people at where I was for my previous postdoc at Rutgers, but also people at CUNY, University of Maryland, Princeton, Amherst, and UCSB. And yeah, this is based on these works, these two works here. So the general outline will go something like this. I'll give you some introduction and some motivation for why we're looking at these kind of systems. And what I'm going to be talking about mainly is some dynamical phase transitions of information. And we'll get into that. And the main object that I'll be talking about is actually these measurement-induced phase transitions, which occur in hybrid quantum circuits. So what I mean by hybrid quantum circuits are I'll have both unitaries and measurements built into the circuit. And we're going to get a percolation-like transition in basically space-time. And then if I have some time, I'll get into the critical properties of this phase transition itself. So this sort of ordered from like understandable to least understandable. So by here, it might get a little esoteric and harder to understand, but hopefully for at least the first two parts, it should be quite comprehensible. But definitely stop me for any questions that you might have to clarify things. So let's start with the introduction and motivation. So why random quantum circuits? So first, let's talk about just random unitary circuits. So let's say I have a Schrodinger equation that's going to act on a whole bunch of qubits that are all in a chain. And I want to evolve them to something like this Heisenberg Hamiltonian. So I can initialize my state in some very high energy state, just a product state of up and downs. And if I just like focus on these two middle guys, as I start to run the Hamiltonian, I run the dynamics, then these two they'll get like entangled with each other. As I keep going further and further in time, that entanglement will grow to the nearest 4, the nearest 6, and it just will keep growing. And at long times, this entanglement is going to spread throughout the entire system, and it's going to thermalize the whole system. So that's sort of just like Hamiltonian dynamics. But like we're going to be talking about random unitary circuits. So instead of Hamiltonians now, we're going to have these purple dots here are like my qubits, and I apply some 2 qubit gates to the nearby qubits. And as I apply these are going to increase. They're going to generically increase the entanglement between these two spins. And we can take this to be qubits or qdits with q internal states. And it turns out that actually, if you take the on-site Hilbert space to q, if you take this to infinity, you can actually analytically write down expressions for this system. So to sort of break down what's yeah, so the gates themselves will be random. I'll describe that a little bit more well, actually right now, because yeah. So these guys they're going to be unitary and chosen from the Haar random distribution. So that's like fancy words, but it's really not that bad. It's basically if you take all of the unitary matrices you can possibly choose, it's going to be some completely uniform distribution over all of the unitary matrices. So I think for the easiest way of thinking about this is the unitary matrices are kind of special. They like live on something like a sphere. And if you want to like randomly choose a point on the sphere, if you like just look at R3 that you embed the sphere in, you can choose a random point in R3 and then project it onto the sphere, and that'll give you a random point on the sphere, completely uniformly distributed. So that process, you can actually generalize that and make any Haar random distribution in a very, very similar way. So does that answer your question?
That actually leads to another question. What is the distribution you choose over the real space?
Oh, you just choose basically for the unitary, so it'll be like q squared by q squared. You just choose a complex number for every entry.
Oh, yeah.
So just completely random matrix.
But the way you described it, you said you pick a point in three-dimensional space at random,
Yeah.
and then project it there. So
Yeah.
I was wondering, what is that distribution used for the three-dimensional space? Is it like Gaussian or what?
Is that what is that called? I think that
Which distribution?
yeah.
It sounded like you induced the hard measure from a different distribution. So I wondered what that is.
It's just so for the Haar distribution, it'll just be it's induced from the distribution for random matrices like GUE, like
Okay.
or whatnot. It's for R3, right? It's just the uniform distribution on R3, but you choose a GOE, and actually what you do is you take an SVD of it and you basically throw out the diagonal part, and then you have a unitary matrix, and that's actually a Haar unitary.
Okay.
So we're going to use this kind of circuit, and we're going to say that one time step is going to be an application of sort of these gates on say the even qubits, and then the odd say these even and then these odd gates. And so it'll be a direct product of all of these unitaries. And then the time evolution itself is just going to be, you just hit with this U of t, which is multiplication of all of these time steps. So what's nice and why we sort of go to this is kind of a minimal example of quantum evolution that has no baggage. There's no like symmetries along for the right. Like all the symmetries are gone. Even energy conservation is gone. So we can just look at the pure sort of quantum evolution in and of itself. And we get things like if we take a cut in the system and look at the entanglement entropy of the left with the right, if we start in a product state, the entanglement entropy starts at 0. But as we evolve forward in time, the entanglement entropy is going to start to increase. And here the blue is e to the minus IHT for some like generic Hamiltonian H, and the red comes from applying these unitary gates. And so it's actually expected that the behavior found here at short times is going to be generic to many body quantum dynamics.
Sorry, the H that you're showing there is the H you defined before, the Heisenberg Hamiltonian?
I think that the Heisenberg Hamiltonian will work there. It will need to not be integrable.
What does this H mean then?
So it's basically going to be something that's not integrable. So there's not like a conservation law that can be written as like a sum of local operators. And in addition to that, you start in a generic state. You don't start like in an eigenstate of the system.
How many gates are chosen for that to make that plot?
For this plot, this is probably I forget exactly for this plot. This probably you mean how many qubits or how many?
Depth of the circuit.
Oh, so the depth is given by the time, and the number of qubits is probably going to be at most 20. somewhere around 20 qubits. And yeah. And so actually, you might you can even see here, since the time is basically one layer, you only get these triangles at integers like 4, 5, 6, whereas this T can be more, can interpolate in between those.
And the statement is that they agree initial times or that they disagree at late times.
So things should generically grow the same at early times. Yeah.
Is that because there is not enough time to appreciate the separation?
Well, you start to, there's a whole bunch of things that happen at late time. Like for one thing, you start to saturate the size of the system, so you can start seeing things like just the fact that you're in a finite system with the numerics. There's only so much entanglement available when you have that. In addition, there's other stuff that you start to see as well that I can't remember off the top of my head about how, like the specific way in which you saturate the entanglement. But let me move off from here. Like that's sort of a bit of a tangent from stuff. So a whole bunch of stuff has actually been done on these random unitary circuits. You can look at things like the operator dynamics. So if you go to something like a Heisenberg picture, you can see how operators are actually going to spread throughout the system. Say you have like a Z operator here, you can see that it's going to become quite delocalized as the circuit goes on. You can actually put conservation laws back into the circuit if you want to. You can make this conserve like the total number of like ones. If this is like 1 or 0, if there's like 3, you can make this actually conserve that as you go forward. You can also do things like flow state dynamics and things like this, all within these random quantum circuits. But the thing that I want to talk about is like how can we suppress thermalization? So this whole process of increasing entanglement is sort of thermalizing the system. And so, given these volume law entangled steady states, is there like a way to actually like kill it off? In a way, can we localize this entanglement so the system doesn't thermalize? And the answer is yes. And this sort of brings me to non-equilibrium phase transitions. So we're interested in these phase transitions that go from like a thermal phase to a non-thermal phase. And the sort of object of interest, the most obvious object of interest is going to be the von Neumann entanglement entropy. So we take a cut through the middle of the system and we ask, is the left-hand side entangled with the right-hand side? And then we compute the von Neumann entanglement entropy to see how entangled it is. If we're in a d-dimensional space, the thermalized state will have a volume law entanglement that scales with basically the size of the system that you've cut off. Whereas when it doesn't thermalize, the entanglement is only going to exist at the boundary, and that is going to be this area law entanglement, L to d minus 1. So we know of one example that actually does this. This goes by the name of many body localization. And the idea here is you have some like very interacting Hamiltonian that you then put some disorder into the system, and then your many body states basically localize in some sense, and you no longer thermalize the system. This has actually been seen in an experiment. So here, this imbalance is like in some optical lattice where like you basically put stuff all on the even sites or the odd sites, and then you just let the system run. And if this imbalance is 0, it means that things sort of spread out to all of the sites. And this delta here is like how much of this disorder you put into the system. When it's 0, things just completely thermalize. They spread out to all from even sites to odd sites. But as you increase the disorder, you see that you actually get stuck. And if you put things in the even sites, they basically just stay there. this is a very high energy state too. Like the all even sites is not like an eigenstate of the system. But nonetheless, things sort of like stick right there. So that's sort of one example that we have. But like, what kind of other tuning knobs can we introduce to see this kind of like phase transition? So one thing was actually seen even all the way back in 2000, where if you have a quantum computer with just unitary time evolution, where with each gate having some finite error rates, eta, you can actually get a quantum to classical phase transition in a noisy quantum computer, where you have like, we go from basically quantum coherent to classical. And so this will motivate us to look at these hyperquantum circuits. So let me get into that now. So there's the questions for the first part there. So yeah, so hyperquantum circuits. So this is the picture here. It's basically kind of the same as before. We have a whole bunch of qubits. We start applying some completely random gates, and then after every layer of gates, we do local measurements with some probability p. So we come in and we basically draw a random number, see if we're going to do a measurement. If we do, then we do a measurement, and we'll measure in the z basis. And now we're going to actually have two things competing with each other. The gates are entangling, and the measurements are collapsing the wave function. They're like killing your entanglement. So when we measure with SC, you say that this guy gets measured. We can break that up into its two projectors, projector on up and down. And this is going to and these are basically going to get applied to this guy based on whether we measure up or down. So this is like just a single shot measurement. There's no expectation value here. You do a measurement, it's going to be up or down, definitely. And so before we had this unitary dynamics, but now we need to think about Born probabilities. So if I take the projector on to say up at this point, then that's going to tell me the probability that I've actually measured up there. And so since I'm doing the circle, I have to figure out with some probability whether it's up. And if it is, then I do the projection and renormalize my wave function. So that's going to be my my update. This can be written out in terms of Krauss operators, where we're going to have both unitaries and then the Krauss operators for each measurement that we do, whether it's projecting onto up or projecting onto down. Everything is going to be normalized by basically the probability that you have that particular set of measurements. So like this M1 could be up, this M2 could be down, and so forth. That's going to have some probability that you measured that, and that's basically your normalization. Right. So yeah, that's the measurement outcomes, and just to write it out explicitly, the probability of that particular measurement trajectory is just the multiplication of all of those probabilities. So the interesting thing that's going to occur here is that we're going to get a phase transition. And so the one thing that I can say out of the gate is if I have no measurements at all, and I start doing the unitaries, the entanglement is going to spread out over the whole system. I'll have a volume law entangled state at the end of the day. However, if I go all the way and I measure every single qubit every time, then I definitely know I have no entanglement in the system when I do this half cut. It's just going to be a completely separable state all the time. So I know those two extremes. So then the question is, does something happen? Does the volume law phase survive when I have a small but finite probability of doing the measurement? And so the answer is yes. In fact, the volume law actually persists some critical value of the probability, where it then goes to area law entangled. So there's a couple of controlled limits that people have taken, and this is like this was seen starting in 2018 by these people here, and a couple of controlled limits that people have looked at is looking at sort of the Renyi dependence when you have completely par random gates. So the Renyi entropy, of course, is defined as like trace of rho to some power n, and you take the log of. And if you take the limit as n goes to 0, you get the Hartley entropy. It turns out that this that you can you can completely figure out what the phase transition is going to be for this particular case. In particular, the Hartley entropy is just the log of the number of non-zero elements of your density matrix. If any of them are non-zero, however small, it contributes to the Hartley entropy. So it turns out when you do a measurement in the system, you can actually think about it in terms of even like an electric circuit where you have like resistors everywhere, and when you do a measurement, it's like you come in and you cut the resistor so that current can no longer flow through the system at all. So that's these cuts here. These are the measurements. And when you measure the entanglement entropy of say this half with that half, you basically want to find the minimal cut to like get to separate the system into two. And so for this guy here, you can follow these measurements down. You have to cross right here, and that will increase the Hartley entropy by 1. And so it turns out that this is actually mapped exactly to bond percolation on a square lattice, which is very, very well understood. And in fact, you can like characterize much about it. For instance, we know that this bond percolation on a square lattice, we know where it occurs with the probabilities. It occurs at exactly 1/2. We also know all of its critical properties. We know its correlation length exponent and its dynamic exponent, which are particular properties of the field theory that lives at the critical point itself. And we know how the entropy actually scales with the log of the system at the critical point itself. So on one side, it's area law. On the other side, it's volume law. But at the critical point, instead of going like L to some power, it actually goes as log of L. Yeah.
I have a question about how the Renyi entropies are calculated. Do you condition on the measurement outcome and then calculate the Renyi entropy and then average that over all the measurement outcomes?
Yeah. So it's weighted. So we actually like use the Born probabilities to figure out like to weight the trajectories more or less. So
it's like a conditional Renyi entropy.
No, it's just a straight up Renyi entropy for the two halves of the system.
The state in which you're calculating the Renyi entropy, is it a pure state?
Yes. Yeah. So sorry, like these are
pure states.
So
It's the post-measurement state.
Yeah. Exactly.
So it is conditional on the measurement.
Oh yes, absolutely.
Right.
And that's actually going to be very, very key. So everything here is definitely it's conditional on all of the previous measurements. If you average over the measurements, actually most of this will go away. You won't see it anymore. If you had the density matrix, if you lost all the information about the measurements, you just had a density matrix, you would not get volume law entanglement. You would just get area law like right out of the gate.
So you did that calculation also.
I don't have to actually. It's actually it's like a 2-line thing even to kind of show it. Well, with a couple of anyway, I can show you if you're interested. But yeah, you can even look at how the Hartley entropy goes with time, and you see when p equals 0, it's an increasing linearly, but when p is like 0.5, it has some different type of growth, which if you put it on a log scale, is quite linear. So it's even scaling with time, like log of t.
Sorry, throw my other
Yeah.
question. You said it's easy to show when you average over all measurement outcomes, density matrix. It's not going to be entangled.
Yeah.
Is that true for all p? So if p is
Yes,
0,
that's
you're not
gonna-
measuring, then there will be entanglement.
Yeah.
Are you saying there's no threshold?
So actually, yeah. Let me just like write down what the argument is here. So there's one step that I haven't actually addressed yet that relate. So you can actually relate this entanglement transition to whether if I put into the system a density matrix, like if that density matrix is going to purify. And so all you have to do is basically
Here.
you keep the good ones. So if I just take a density matrix, which is 1 over e times the identity, so it's just like infinite temperature density matrix. If you take this guy and just the fact that the fact that I sum up over my various measurement outputs for the Krauss operators, this is one. If I evolve this forward in time, it's going to remain 1, like no matter what. And so that like the extra leap is that I haven't actually explained how this is related to the fact that we purify. This would purify for the individual measurement trajectories. That's how you see it. Whereas here, this will just remain 1 forever. Right. So it turns out that here if I sit at 1/2 at the transition point itself, then my system is actually described by something called a logarithmic conformal field theory, which people have spent a lot of effort figuring out the math behind. And it turns out that that's not going to be written in terms of like log L plus some function that depends on L and some critical exponents and things like this. And using this, you can collapse the data and get nice collapse to figure out all the critical properties you want of the system. Another controlled limit is actually going from qubits to qdits, where we have a q-sized Hilbert space that we put into the system. And people have shown here that you can do a replica field theory to get this like non-trivial stat-mech model, where like you have q replicas. So you take the system and you actually copy it a number of times. So if you're doing the Renyi entropy, you actually have to copy it n times, and then you're doing a disorder average, and so you have to actually copy it n more times. So you have this n times n kind of a number of replicas. And if I take the little q to infinity, it turns out that this becomes a q-state Potts model, which people have been studying for quite a long time as well. And if you take this big Q to 1, you get back percolation exactly. So we even know that like if you have a large on-site Hilbert space, it'll be the same as percolation as well. Another kind of controlled limit, but that you do have to put on a computer, are stabilizers. So here we can do numerics on stabilizer circuits, where we actually choose these gates to be from the Clifford group. So these are special unitaries that only send polystrings to polystrings. And so we randomly sample from the Clifford group to do this. One kind of nice property of this is that if I'm doing just Clifford gates, there's no Renyi index dependence. If I write any density matrix and I diagonalize it, all the eigenvalues will be the same. And as a result, if I raise them to the nth power, it doesn't really matter. They're approximately like just proportional to 1. And so there's actually no independence. So people have done this, so you actually find a different thing from the Hartley entropy for the hard case. You actually find a PC around 0.15, and there people have again seen that the entanglement entropy is going to scale like log L. I don't have to put an n here because it's the same for every n. And you get a slightly different value of the coefficient for the log L when you do with percolation. So that's all well and good, and this has been extended. So you can have you can do it with just some chaotic many-body Hamiltonian. You can actually relax the projective measurements and just do weak measurements on the system, and you see very similar stuff as well. You can also do models with like fully like non-commuting projective dynamics, and you can even drop this local thing and consider just long range interactions, and so you no longer have volume law and area law, but you do have this. It becomes a purification transition now, which is kind of what I was describing before. So in the statement there is you put in a mixed state into your system, and over here that mixed state will basically persist for a very long time. It'll persist exponentially long for exponentially long times. It'll remain mixed. Whereas on the pure side, it'll actually become a pure state. So the density matrix will go from having a rank greater than 1 to rank equal to 1, and it'll do that in a time that's just that's proportional to the size of the system L. Whereas here it takes exponentially long times to purify. And it turns out that this actually works just as well for the one-dimensional case. And there you actually have this correspondence I was mentioning, where like the entanglement transition that you see there is the same as the purification transition. That correspondence will most likely, I think, break. I think it's been shown that it breaks down to higher dimensions, but for like 0 and 1 dimensions, it works pretty well. So the summary so far is that we have these controlled limits that yield a transition in the percolation universality class. So for the stabilizers, there's like some differences, like how the log L, the coefficient of the log L has now changed from percolation. And we also have seen that the transition persists in a number of different models and in a lot of different settings. So now we're interested in like how is this transition different from percolation, or is it different from percolation? If we were to look at the fully Haar problem, not the Hartley entropy anymore, but actually look at the other entropies like von Neumann entropy and things like that. In particular, how do we characterize this measurement-driven like phase transition between the ergodic or volume law entangled phase to the area law entangled phase in this fully quantum limit? So that I'll start getting into the actual critical properties of the measurement-induced phase transition. So the first thing that you might do going and looking at some conformal field theory stuff is to say, okay, well, I need to find my critical point PC, and I know that my entanglement entropy is going to scale something like it did for Hartley, some alpha times log L plus some some function that depends on p minus bc times L to the 1 over nu. And you can do some scaling collapse. That's not so bad. However, you actually find when you do this, you get a nu of around 1.3, which is close to percolation. But you find that there's a lot of wiggle room. There's actually quite big error bars on this nu. So like this whole just kind of trying to find this log L and subtracting it off, it didn't actually seem to work extremely well in the end. So So now, if we're just going to think about these about 2 equals 2, just the qubit gates, just with the hard gates, we're gonna have to use numerics. It's going to be actually on the pullover space as well, because we're going to have volume law states. So we can't use any method that's going to take advantage of a very long entanglement to let us get to bigger sizes or something. And we're going to ask, like, does the fully quantum problem belong to a different universality class? And so we're going to need an unbiased estimate of the critical property. So we want to kind of avoid this kind of assumption here. So the first thing that we found was that if you take your system, give it periodic boundary conditions. So there's qubits. You can think of the qubits existing all along this boundary here and evolving along in some cylinder. You can calculate this tripartite mutual information, which is a very funny quantity. It's like a mutual information, only even more complicated, right? You have an A, a B, a C, an A union B, an A union C, and a B union C, and then all of them put together. But it turns out this would correspond to some very complicated like 6-point function in a formal field theory or something like this. But if you bound all these to be L/4, all of these little sections, things are
I think this tripartite information, if you draw a Venn diagram with 3 of them, is that the intersection right?
Actually, is it the intersection down the middle? It might be. I do know that, like, so it ends up being generically negative, but it can even be positive. It's like, so I don't know if that, like, yes, like mutual information has to be positive, right? This quantity can actually not actually be. Yeah.
I seem to remember something like that. You were not in your head a little bit.
Yeah, that's all I think.
But it can go negative, right?
Well, this is actually generically negative, it turns out, or it just sometimes goes positive. Like you subtract off too much. And if you just put like a completely hard random state in here, it'll most likely be. So you can actually show that this is going to be L independent at a PC, and we'll see this mostly numerically. And the way we kind of see that is we're going to have we have this I3, and we have 8, 12, 16, all the way to 24 qubits. And if you look at all these curves, they're intersecting kind of at one point here. 8 is kind of a little bit off, but there's finite size effects that are going into account there. You see that you actually get a kind of a nice crossing. So here, this is without 8. I believe the rest of them are all there, and you get a nice crossing at about 0.117, which is different from what previous. So there's work before us that actually put DC to be quite a bit higher than this, but we find that this actually is quite robust to even different types of measures of the transition. So in order to benchmark things, it's good to compare with the Clifford circuits, because those, when you simulate them, you can get to quite large system sizes. With the Clifford circuits, you can get to hundreds of qubits. For us, we can get up to 24, but we can take the Cliffords, knock it all the way down to 24, and see if we get a good crossing, and see if it matches well with the higher, when those go to higher levels. Turns out that actually works quite well even for the Cliffords. So as a benchmark, we can then use that to compare to hard. Say this is probably a pretty good value of the critical point. So here 0.154 and here 0.17. And so we can even map this out with the Renyi index. So yeah, you can calculate I3 by just naively throwing in all of the Renyis that you want to, and you can find PC for all of these. There's one thing that actually constrains this, which is kind of interesting. All the Renyis must satisfy this inequality for the n's greater than 1. And what this actually means is if you're going to have a volume law entangled state, then it has to be true for all of the Renyis at the same time because of the way that S infinity is going to scale. Or the way that Sn, if Sn scales like L and S infinity doesn't, then there's going to be a particular value of L that violates the inequality. So that sort of tells you that if one of the Renyis is in the volume law entangled phase, then they all are, at least for n greater than 1. So it turns out that we don't have to separate out any logs anymore. We can actually just separate this. We can actually collapse this onto one function. And when we do that, we get a nice collapse with a good value for the PC and the correlation linked exponent of like 1.2, which is within the error bars of percolation still, which is also different from what people previously found. People had a larger value of PC, and their critical exponent was much higher than percolation. And so we can even look at nu for all the Renyi indices, but for various reasons, these should also be the same. And yeah, this sort of comes from the fact that the correlation links to kind of go to a constant to still satisfy this inequality, which means if you do have different correlation links for every value of the Renyi, then you would violate the inequality again. But actually, this is actually quite a good measure to look at the transition in a lot of different systems. There's another one that I actually personally find a little bit more intuitive. So it's developed by Gollins and Hughes, called the order parameter. And what this basically does is it comes into the system, and you do a measurement, but then you bring in another ancilla qubit, and you maximally entangle it in a Bell state with just this one qubit that's already in the system. And then you just look at your ancilla and you ask what its entanglement entropy is. And so the reason I think this is quite intuitive is it gives you a good idea of what's actually happening with this transition. So it turns out on the volume law side, if you couple in this ancilla, it's going to have some entanglement entropy, and that will be a finite value for exponentially long times on the volume law side. So you took a bit of information, you put it in the system, and the system lost it, and you're not getting it back. It's sort of just somewhere encoded complexly in the system. However, on the area law side, it turns out that when you put this ancilla in, at a certain point, it's going to actually disentangle from your system because of your measurements. And when that happens, you basically lost that bit of information that you put into the system. And so that's really why it's kind of a transition that's occurring in the information itself. And to bring that back to what I was talking about with the density matrix, once I put this ancilla in, if I were to trace out this ancilla, I'd have a density matrix of my circuit. It would have rank 2 because there's only a qubit that's attached to it. But at a certain point, that rank 2 would have to go to rank 1, and that would be the same as the entanglement transition. So that's also kind of why this is an order parameter. It remains sort of 1 on one side of the transition and goes to 0 on the other. So we can look at the reduced density matrix of this ancilla. And as I was just explaining, it remains entangled on the volume law phase and vanishes in the area law side. So here's just a plot of 2 extremes. So if P is like 0.5, I put in so I measure one of every 20 qubits every go. Then the entanglement entropy stays pretty saturated. It will actually die off at exponentially long times, but it stays pretty close to some value. Whereas if I crank up to dot 3, it'll go to 0 quite quickly and vanish. So we can actually also, we can track this in a more systematic way, looking again at systems of like 8, 12, 16, and 20 qubits. And those also have a very nice crossing. This crossing occurs extremely close to what we got for I3 as well. And we can take this and fit it as well to some to get some correlation to get the correlation linked exponent and the dynamic exponent for how this this evolves. So the PC is again about 0.17, and we can first like fix P equals PC, and we can collapse everything in time. So this is like for various system sizes. You see that the curves are separated, but we know that things have to scale as t divided by the size of the system to some power. And we can find that power is very, very close to 1, which you kind of expect. You expect there to be kind of like time and space should be very, very similar to each other at the transition point, and that's actually characterized by z equals 1. That means t over L is kind of like a constant in some sense, like your speed of light, your speed of information. You can also look at things like correlation functions. So if you put in two ancilla qubits, you can connect them up and actually see how the mutual information of those two qubits, how that evolves. It's going to start it's going to start at 0 because there's no correlations between these two ancilla, but it'll develop correlations as the circuit progresses. It turns out that this can be written out in the conformal field theory as well, and has some universal exponent eta that it goes as. And for Clifford and Parr, we can see very similar things. It starts at 0 and it sort of starts to go up to some value, and these are the collapse curves, and these are the non-collapse curves here. And we get eta about 0.22, or for Clifford and about 0.19. But for percolation, this should be about 0.21. So again, this is also quite close to percolation. So just as a summary of the critical properties, and I think that I'll end here and just have a little bit of a teaser of the last part. But so we have all these. So this is even for various Renyi indices, and for Clifford and for percolation as well. So the various PC values, you can see that the critical exponents nu and eta, they're all quite close to each other here. So percolation should be, we know analytically it should be 1.33 or 4/3, and we also know that it should be like 0.21. I think 5/24. I think is the analytic result. And these are all quite close. So like, are we actually seeing something that is in fact different from percolation? And one little tease of the fact that we might not be is if we look at how the entanglement entropy scales as log L at the transition, we actually find that that we get something that's going to differ from what you expect from just regular conformal field theory. You get some independence here, and this alpha value for Clifford and for Parr quite differ. So for a conventional unitary CFT, we expect this alpha to go as 1 + 1 over n. So this is actually some of the first hints that we're not actually seeing a regular conformal field theory at the transition. That's one of these more exotic logarithmic conformal field theories, which if you know about, they have zero central charge. So I think that I will actually end there, since I've gone even a little bit over. There's some interesting stuff that actually does completely separate you from percolation that you can pull out of multifractality, but I think I'll leave that just to end here. Thank you.
questions for Justin?
Let me ask a quick question. So you were mentioning the conformal field theory many times.
Yeah.
So mathematically speaking, if we have the circuit right here, like how would the conformal field theory run? Or like how would you, why would you use it in order to describe this system? Like when you look at the Hamiltonian, is there a way to like do a neat field approximation or something?
Yeah. So there isn't a Hamiltonian, right? It's going to be these circuit elements. One thing that you can do, like all these analytic treatments, map things to a problem that's basically percolation, which then has a well-known conformal field theory at the transition. But that doesn't help us with the qubit case. So there, it's actually mostly empirical. Like we're doing these numerical experiments, and we're actually seeing that things fit conformal field theory quite well. We get these critical exponents for how things scale and at the transition, and that seems to match the water conformal field theory. So in some ways, the logic might be a little bit backwards in the way I presented it. Is that we have this stuff that's sort of confirming or suggesting that we have a logarithmic conformal field theory.
Would that be different from the Randall Ginsburg theory? Or?
Yeah. It should be quite different. Though, like it's possible that you might be able to have some. I mean, it'd be great to have an analytic model of exactly how this works, and maybe it would have some kind of symmetry breaking. The trouble is that we don't exactly know the degrees of freedom for the conformal field theory, because it's we're putting some information in the system that's getting completely scrambled up. It's either lost or it goes away. Those are like the two transitions. It's either like spread out in the system or it goes away. This somehow there's some degrees of freedom that are controlling that we just don't have a good handle on. And it's one thing that we're trying to figure out.
So I want to come back to the beginning of the talk just to make sure that because when you introduce these random circuits, my internal question was why? I mean, what is that interesting for? And then is your statement that should capture genetically the evolution for genetic Hamiltonians?
Yeah. So if you have a Hamiltonian that has like very few conservation laws, but that's one that's a chaotic Hamiltonian, then this should be quite a good model for chaotic.
Is there any control of that? Because Hamiltonians are. You can write really Hamiltonians.
Yeah, they come in all shapes and sizes.
Sure. Right. So, is there any control about that?
So I'd say mostly it's that these various quantities that we're looking at, like for instance the entanglement entropy and whatnot, they seem to match quite well, like how entanglement spreads throughout the system, or how things are like basically thermalizing, which is the context in which a lot of these chaotic Hamiltonians are being looked at. So if you have an integrable Hamiltonian, it won't actually. Then this would be a bad model for an integrable Hamiltonian, because in that case you can get more or less like stuck, and the entanglement might not spread like maybe it spreads like a log L or something like that.
The question is there a mathematical control about which family of Hamiltonians is?
Yeah, I'd say it's basically just the non-integrable ones, like where you can't write it down. Like you can't write down the like if you have objects that commute with the Hamiltonian, they can't be written down as a sum of local operators. For instance, maybe even a little bit more than that is needed, but I'd say like that as a minimum you would need that.
Way to understand, or do you expect the different critical probability values to be different for the Renyi entropy considered?
Sorry, I didn't hear you.
The critical probabilities you got versus the Renyi index are slightly different. Is that expected? Or?
Oh yeah, that's I would say that we calculated all of them because like we wanted to be completely unbiased about it, but I think that let's see. like here. So they're all like quite close to each other, right? So like this is 1.3 plus or minus 0.1, 1.4 plus or minus 0.1. So they're actually, I think all of these here, 1 up to infinity, well, 1 is accepted from the argument I was giving with the inequality. 2, 5, and infinity should be the same. We just calculated them all because we could separately, but these should they should match within the error bars they do. 1, it turns out that it looks like it does match with the other ones, but it doesn't. Like we don't have proof that it has to, at least within the error bars.
So to do your simulations, what, 20 qubits? Right?
Yeah, like 24.
You have to use a supercomputer? That's
24.
a lot.
24, I think we can. Well, so we do put it on a cluster. I don't know if we need necessarily a high memory node to do 24. I don't know. I should be able to like kind of do that on my computer.
So it seems like the next step, given that we have quantum computers, is that you could actually try to do this.
Yeah.
with existing quantum computer. That could be an interesting. Do know ways to calculate Renyi entropes, integer Renyi entropes efficiently.
By replicating or by
By replication.
Gotcha. Yeah. No, that
Might be something interesting.
yeah, I think that could be very interesting. The one thing that sort of there's been some trapped ion experiments by Chris Monroe that's looked at some stuff related to this. The thing is, it's a little bit tricky because like the moment that your measurements aren't like you have to keep track of all of your measurements, because the moment you lose some fraction of them, this whole business goes away.
Right.
So
we have to calculate some conditional.
Yeah, exactly, which is exactly what I think that they try to do. But like slight errors in that can also throw things off. I mean, it could throw off like the sharp properties, but I imagine things would just be like rounded out by having some like finite error or things like that. So, source of dephasing or decrease.
How long did it take to do those calculations on the cost?
Yeah, so the thing that actually takes the longest is to get good statistics, because we really need to like run different realizations for like sampling over R and also measuring trajectories themselves. We sort of do all those at once, and each individual one is probably be done in a couple of hours, but you might need to do like 2,000 or 3,000 to get good statistics. So that can take a while.
All right. Well, thanks for a very interesting talk.